we have discussed about the structure and isomerism of alkenes. Now we will discuss about their preparations. So there are various methods of preparation of alkenes. First of all, we will discuss the preparation of alkenes from alkynes. Alkenes are formed due to the partial reduction of alkynes. So let's start. Preparation of alkenes. Okay. So the first preparation is from alkynes. So alkenes are formed by partial reduction or partial dihydrogenation of alkynes with calculated amount of reagents. Okay. So partial reduction or partial dihydrogenation of alkynes with calculated amount of reagents. Okay. Why calculated amount? Because if we perform complete reduction, then alkynes will form alkanes. So alkynes, if we perform complete reduction, then it will form alkanes. But for partial reduction, they will give alkenes. Okay. So for the conversion of alkynes to alkenes, there are two methods. The first one is by Lindlar's catalyst. So Lindlar's catalyst is basically hydrogenation in presence of metal catalyst. There are various methods for hydrogenation in presence of metal catalyst, but specifically Lindlar's catalyst is H2 in presence of palladium charcoal, CaCO3 and quinoline. Okay. Here quinoline is poison or deactivating agent. Like we had discussed that for the conversion of alkynes to alkene, we require partial reduction. So we need a reagent which deactivates the reaction, that is, controls the reaction in an intermediate position. For this we require some deactivating agents which are also called poisons. So quinoline is one such poison. The important feature of hydrogenation by Lindlar's catalyst is that this method produces alkynes to cis alkenes. Okay. Only cis alkenes are formed by this method. Trans alkenes will not form. So, what is the reaction? Let's say this is the alkyne undergoing hydrogenation. There is palladium charcoal, calcium carbonate and quinoline. So, this will give this, okay, that is cis alkene. This was the alkyne, this is cis alkene. Now, we will see the mechanism of this reaction. Okay. So, for mechanism, we have a metal catalyst here, right. So, we have a metal surface. And there is hydrogen and there is the alkene. Now, in the first step, they will undergo adsorption. That is, these compounds will adsorb in the surface of the metal. So, it forms like this. Okay. And the hydrogens also get adsorbed. Now, in the next step, this is called desorption. Now, the hydrogens that were adsorbed in the metal surface, they will form bond with the carbon and the resulted alkene will be desorbed from the metal surface. So, the metal surface is left as it was and we get an alkene. Okay. So, this was the mechanism for hydrogenation of alkynes with the help of Lindlar's catalyst. Now, the second method of preparation of alkenes from alkynes is the Birch reduction. But before starting Birch reduction, we need some insights into the stability of alkenes. Okay. So, before starting Birch reduction, we will read about stability of alkenes. So, the first thing is more the number of alkyl groups attached to the carbon-carbon double bond, higher is its stability. Okay. This is due to hyperconjugation. Because let us see an example. Okay. Now, hyperconjugation can occur like this. Okay. So, this is the hyperconjugated structure. So, the number of alkyl groups are more, then there will be a greater number of hydrogen and greater number of hyperconjugation structures. Okay. So, since hyperconjugation increases with the increase in the number of alkyl groups, so more number of alkyl group means the more stability of the alkenes. The second point is that trans is usually more stable than cis. Okay. Trans is usually more stable than cis. Why? Let us say this is cis. Okay. So, the two bulky groups are in the same side of the double bond. So, there will be some steric hindrance. But if we look at this compound, then the bulky groups are on the opposite sides of the double bonds. So, there will be less steric hindrance. Okay. So, trans is usually more stable than cis due to lower steric hindrance. Okay. So, now we will study about the Birch reduction. So, in Birch reduction, the most important factor is that Birch reduction forms alkynes to transalkenes. Okay. In Lindlar's catalyst, we were having cis alkenes. In Birch reduction, we will have transalkenes. And what are the reagents? Reagents are lithium or sodium plus liquid ammonia. Okay. Lithium or sodium metal plus liquid ammonia. This is the reagent of the Birch reduction. So, if this is the reaction, then this will form okay. So, this alkene will be formed, that is the transalkene. So, we will now see its mechanism. Okay. So, let us consider this. Okay. Now, we have sodium metal, for example. So, sodium metal can form Na plus and 1 electron. Okay. So, we have 1 electron in the system. Now, this electron attacks on this carbon and 1 pi bond breaks like this. So, what will be formed? One radical here and one radical here. Now, this can be in two forms. Okay. These are the two possibilities. This is cis, this is trans. Now, in cis, again according to steric hindrance, trans is more stable, we know that. So, by preference the reaction will favor the trans isomer. Okay. Now, let us take the trans isomer. Okay, I am sorry, here I have done one mistake. So, this bond is having homolytic fission, so two radicals, but initially this electron had attacked on this carbon, right. So, it will have a minus charge overall. Okay. Sorry, please correct this. This will have a minus charge. So, we have this compound, right. Now, we have ammonia in the system, NH3. We can write this as NH2 and another H. So, now this minus charge will take up this hydrogen and so this forms along with NH2 minus. Okay. So, we had sodium plus in the system, by the way. So, again there is another sodium plus, so another electron will be there. So, again it will attack here. So, now any bond will not break, but a negative charge will be formed in this compound. Again we have NH3, it will take up this hydrogen and eventually we get this alkene. So, this was the mechanism for Birch reduction. So, in this case trans is the major product and for Lindlar's catalyst cis alkene was the major product. Why am I saying major product? Because in this case trans can also form as minor, and here also cis can be formed as the minor product. Okay. Now, any reaction is not 100% stereoselective. There has to be a major product and a minor product. Okay. No reaction is 100% stereoselective, because although one product is favored, but there is always a slight chance of the formation of the another product. Like for example, in the Birch reduction, the trans component was more stable, so it was more favored. But will the cis component not form at all? That is not the case. The cis compound will also form, but in a very less quantity. So, always one product will be the major product and one will be the minor product. This is known as stereoselectivity. We will discuss more in details about stereoselectivity and stereospecificity in the next lecture. Thank you.